This is a 100-watt laser. You can use this to cut through wood, rubber, even granite, and it is massively dangerous. You can very easily blind yourself with it, start a fire. Not a toy. This is a 100-watt light bulb. Also not a toy, but you're not going to use it to slice through anything. I suppose you could injure yourself with it. I mean, I guess you can injure yourself with anything, but it's a lot harder to hurt yourself with a 100-watt light bulb compared to a 100-watt laser. You don't need special eye protection to be in the same room with it. You're not going to set things on fire by accident. It's lower risk. But it's worth asking why. They're both 100 watts and they both put out light energy. So why is it that the laser is a powerful and dangerous tool and the light bulb is just something that produces light that you have in your house? Here's the title card. I guess you could call this episode Why You Can't Cut Steel with a Halogen Light Bulb. Maybe you've never wondered that, but I wondered it, and so I thought I'd share what I found. There are a lot of descriptions out there of laser light, and they'll usually say what is unique about laser light without really specifying like why that would actually be something special. I'll just rehash that here quickly. If you look at a light from a light bulb, you would see photons emanating from the source. So here's an illustration of that. You can see wavelets flying by. And while they do have a spectral distribution, there's some degree of randomness. There are variations in frequency, there's variations in the direction, there's variations in the phase. Now, light coming from the laser, on the other hand, is referred to as being coherent. So what that means is the waves are all the same frequency, they're the same phase, and they're the same direction. Now, they may be moving in a non-divergent parallel path, or they may diverge, or they may converge, and you can switch that up with lenses. But fundamentally, they can go off and be a parallel beam nearly forever. I mean, not actually forever, but for a very long time. Or they can be focused down to a point whose size is limited only by the diffraction limit of light. And now these are the properties of an ideal laser. And the reality is that lasers vary in quality. It's not actually enough to say this is a 100-watt laser, it's more useful than a 50-watt laser. The quality of the laser light matters as well. How close it is to this ideal of perfect coherence, no variation in frequency or direction or phase. But for now, we'll just pretend that everything is either a perfect laser or a conventional light source. So this is the difference between them, but why does that mean you can burn a hole in steel with a laser light and you couldn't possibly do that with a light bulb? As is often the case, there's a really complex roundabout way of explaining this, and the complex way is actually not very profound, to be honest. But then there's also a simple way that you can explain it, which is very profound. So let's do the non-profound explanation first. So if you want to create incredible amounts of heat at a point, you want to focus the light energy on as small a point as possible. And laser light pretty much by definition is able to do that. Not to an infinitely small point, which is impossible to do for a wave, but rather to a point that's around the same size as the wavelength of the light that you are using. But a laser can do that, and it can put all 100 watts, if it's a 100-watt laser, for example, on a circle that is around, 1,000 to 2,000 nanometers wide. That is just an incredible amount of power on one tiny, tiny spot, until that spot is going to get really, really hot really, really fast. So it's not surprising that that can actually vaporize steel and cut through steel. When you've got energy focused that tightly on a small spot, there's a lot of energy coming in, and it dramatically outpaces the thermal conduction of energy taking heat away from the spot. So you've got more energy going in than coming out until the temperature rises very, very quickly, until the material vaporizes, and you cut this very thin, precise hole. Now we know, because we talked about laser light being coherent and parallel, that you could do that with a laser. But could you do that with a regular light source? Could you do it with, a light bulb? What would it take to do that? So first you would have to focus the light using a lens, which in itself is an incredible passive device. Lenses are actually pretty amazing. This is just a quick digression, but if you think about the light in a room, it's just random photons flying here and there, this way and that. And if you just sample the photons, you can't really get an image out of that. Like if you just leave a piece of photographic paper out, you don't see an image of the room. It just turns white because it's being hit from photons coming from all different directions and all different angles. But a lens, just by the way that it's shaped, just purely through its geometry, will essentially reassemble the photons that are going off in all sorts of random directions into this simulacrum of what they originated from. And it reforms an image. So you might think that you could reform all the energy that came out of the very hot filament in the light bulb and use that to burn a hole in something. But unfortunately, the rules of geometric optics make that exceptionally difficult. The size of a focused image can be larger or smaller than the original image, and the ratio of size is equal to the ratio of the lengths of the source and the focus from the lens. So, for example, if the focus and the source are the same distance from the lens, you could only focus it down to the same size as the source, which a filament in an incandescent light, for example, it's very small, but it's not that small. It's not nanometers small. If you do want to focus it down to that extent to make a small point, you would need to move the source very, very far away from the lens. But then if you do that, now you only capture a tiny, tiny fraction of the light itself, only the amount that's subtended by the lens. So it becomes self-defeating. The energy is more tightly focused, but then there's less energy coming in. It's actually more practical to just forget about the lens completely and use whatever energy source you're using to generate the light or the energy to directly cut the material itself. So for example, some of the brightest light sources around are based on electrical arcs, but it doesn't make sense to capture this light with the lens and project it onto metal to cut it, when instead you could just directly jump an arc onto the workpiece made of steel. And that's what a plasma cutter does. Same thing with filaments. Nobody's ever used a hot filament in a light bulb focused on a point to cut something, but people do use hot filaments to cut styrofoam directly using heat. I can only really think of one time that focusing non-laser light onto a point has been used for a practical purpose. This actually sort of works for the sun. So the sun is super, super bright and super, super far away. So you can get it down to a relatively small point that still has a reasonable amount of energy. So for example, the sun is about 150 billion meters from the Earth, and it's about 1.4 billion meters across. We'll just round that to 1.5 billion meters to make the math easy. So if you assume that you focus it onto a point that's 10 centimeters from the lens, then the point would be about 1 millimeter across. Now, because there's a lot of solar energy on a sunny day, depending on the latitude and conditions, that can be hundreds of watts per square meter. You can really put a lot of energy in a small space. And I've read actually that focused solar energy was actually used to weld copper sheets in Italy during the Renaissance. I thought that was super interesting. And nowadays you can often see videos on YouTube, for example, of people using Fresnel lenses to melt metals and rocks and things. I think there's a whole channel that does this. It's pretty cool. And it just illustrates how hot you can get things just using solar energy. But really, the best solution is to just use a laser, okay? Because you can focus it on a point that's much, much smaller than the focused sunlight. And so it's just going to work a lot better. It's going to be a lot more precise. So that's the roundabout way of explaining why lasers are so useful. But let me give you an alternative explanation, which is way simpler. The alternative explanation is that lasers and common lights are just totally different forms of energy. Sure, it's true that they're both light, they're both electromagnetic waves, but actually they're just totally different, so we should not have any expectations that they should have similar capabilities. Let me explain what I mean by that. So here's an analogy. So suppose you have a ball that weighs 100 grams, and let's say that you add 10 joules of energy by throwing the ball. So, kinetic energy, it's 1/2 mv squared, so that means that the velocity is going to be around 14 meters per second. Now, if that ball hits you in the face, if it's going 14 meters per second, that's very bad news, okay? It's really going to injure you. Now, suppose instead you add 10 joules of energy, just like you did before, but you do that by heating the ball up. So if you assume the specific heat is around a joule per gram per degree Celsius, it's just a ballpark number, no pun intended, that would mean that you would heat it up by 0.1 degrees centigrade. So if you do that and you held that ball up to your face, slightly warmer than the ambient temperature, it's not going to cause a problem. It's not going to cause burns or injury or anything. So in both of those cases, we added kinetic energy. So heating up the baseball added kinetic energy to all the molecules in the ball. They started moving back and forth more vigorously than they did before. But in this case, we would immediately recognize that even though they're both the energy of motion, they are just qualitatively very different. The motion of the thrown ball involves all the atoms in the baseball moving slightly faster in the exact same direction. Whereas with the warmed up ball, the atoms are moving slightly faster in random directions. Both of these are kinetic energy, but one's random and one is not random. And that is the difference between work and heat. And this distinction between random and non-random energy, the distinction between work and heat, that is a much, much more fundamental distinction between different types of energy than labels like potential energy or kinetic energy or electromagnetic energy, etc., etc. But why should we think of heat as being limited to just the kinetic jiggling of atoms? After all, matter can transmit or lose or gain heat via radiation, and so clearly photons are in thermal equilibrium with matter that has kinetic motion. So wouldn't it be more accurate to think of heat as chaotic energy in any form, whether that form is the random jiggling of molecules or the random frequency and phase of photons? So by analogy, laser light is like the baseball flying through the air, and the incandescent light is like a tepid baseball. So really the question didn't even make sense to begin with. Of course they don't have similar capabilities because they're totally different forms of energy. One is work energy and one is more analogous to heat energy.